source is something that looks like this. The voltage of the source is some amplitude, right, times sine of omega t. And then you could also have some phase angle phi, right? Or it could be cosine omega t plus phi. So some kind of sinusoidal varying AC source. Now, if I connect the resistor to it, I want to know what the voltage of the resistor is going to be, what the current in the circuit is going to be. And then if I connect the inductor to it, what's going to happen there? Then if I connect the capacitor, what's going to happen to that circuit? So this is called force-driven oscillation. You're driving the oscillation of the resistor with some AC source, and then you're analyzing what happens to the voltage of the resistor and the voltage of the inductor and the voltage of the capacitor, and also the current in the circuit. The current in the circuit. And then we could also analyze the voltage of each one. So with the resistor, the circuit is going to be like this. Voltage of source minus IR is equal to 0. So if you only have a resistor, you just have voltage of source and the minus IR is equal to 0. So therefore the current in the circuit is simply going to equal the voltage of the source over the resistance. So if the voltage of the source was A sine of omega t plus phi, the current in the circuit is going to be, instead of A, let's write this voltage max, Vm. So volt Vm over R. So voltage of the current is going to be simply voltage of the maximum voltage divided by R times sine of omega t plus phi. So what we say to that is that the current in the circuit is in phase with the voltage of the source. And of course, voltage of the resistor is equal to the voltage of the source, because that's the only thing in the circuit is the resistor. So then we say voltage of resistor is IR, and then we say voltage, just multiply this by R, and you have voltage of the resistor is Vm sine omega t plus phi. So if we were to draw this on an oscilloscope, we would say the voltage of the source is some, let's just say for now that the phase angle of the source voltage is 0. So it starts as a sine function. Then it goes up, down, like that. So that would be the source voltage. And then the resistor voltage will be identical to the source voltage. So then we could draw that with this pen. The resistor voltage equals to the source voltage. VR equals V source. And then the current in the circuit looks like what? The current is in phase with the source voltage and the resistor voltage. The current is in phase with it, but it's just off by Vm over R. So the amplitude of the current is not the same as the amplitude of the source voltage. So it looks something like this. You see? So whatever the resistor voltage is doing, the current is doing the same thing. It goes like this, like this, like this, like this. So it rises with the current rises with the voltage of the resistor, then drops. And when the two are equal to 0, when one of them is equal to 0, the other one is equal to 0. Then we can express this with what are called phasor diagrams. Phasors. We could say this is the voltage of the resistor, which is also equal to the voltage of the source. And then the current is in phase with it. So what phasors are is a rotating vector, right? And then the angle of this vector is omega t. It's this portion, right? It's this portion of the sine function. So then as t is progressing, this vector is rotating counterclockwise. And then the vertical component of this phasor, right? So if from here to here, the amplitude is Vm, right? The vertical component of this phasor represents the instantaneous value of the source voltage or the resistor voltage, you see, the vertical component. So if it starts like this, if I said, remember I said the phase angle is 0. So the phasor will start like this, and that means the source voltage starts at 0. So then as it's progressing, the source voltage reaches max when it reaches the vertical position. Then it goes smaller, smaller, then 0 again. Then as it's rotating negative, 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 which represents going down into negative regions, you see. So this is another visual way of representing what you would see on an oscilloscope. It's a more vector method of representing the oscilloscope. Okay, now let's see what would happen in an inductor. So then you do here, you do the voltage of the source minus, instead of the voltage drop across an inductor is L di dt. So instead of IR, it's L di dt. So then I have voltage of the source is Vm sine omega t. So again, assume that the phase angle is 0. And that's equal to L di dt. And then dt can go over there. L can come down here. Vm sine omega t dt over L. That's equal to di. So now in order for me to calculate the current as a function of time, I have to integrate this function. So integrate to get the current as a function of time, the current in the circuit. Okay, then I have I of t is equal to, and then the integral of sine is negative cosine, right? Vm over, and then the omega comes out, Vm over omega L, and then negative cosine omega t. Okay, so you see what's going on is kind of weird. So the current, if the voltage is, of the source is behaving as if the voltage of the source is behaving as sine omega t, the current is behaving as a negative cosine. So then what would happen to the oscilloscope? So then once we get the current as a function of t, we can just do L di dt and get the voltage across the inductor. Well, if I do L di dt, if I do the derivative of this multiplied by L, it's going to get me back to what the voltage of the source is. So then the voltage of the inductor is just going to be whatever we started with, Vm sine omega t. So then the oscilloscope would show us something like this. The source voltage is like this. This is voltage of the source. And it's also equal to voltage of the inductor. Of course, I'm assuming inductor is the only thing in the circuit. So then what would the current look like? It would look like a negative cosine function. So that would be negative cosine looks like this. Something like this. Starts at negative, it starts at the most negative, then it goes like this. And when this reaches 0, it goes like this. And it goes 0. So in other words, when this is 0, this is its minimum value. When that reaches max, this reaches 0. When this is 0, that reaches max. And when this reaches min, that reaches 0. And then when that reaches 0, this reaches its min again, like that. So the current would look like that. Okay, so how would we write that so that we can compare the two? How would we rewrite that? So we could rewrite negative cosine as sine. So we could write it like this. Vm over omega L. We could write negative cosine as sine omega t minus pi over 2, I think. Or should we do plus pi over 2? So we could kind of think, because they're out of phase by pi over 2 radians from each other. So the way to do this is to say, if I can rewrite this negative cosine function and in terms of a sine function, and then find out what phase angle I need here to give me the same results. So if I put, let's say, t is equal to 0, this is going to give me cosine 0, which is 1, and then, so it's going to give me negative 1. So if I put 0 here, sine of negative pi over 2 is negative 1. So that's it. So this mimics that same function as that. So then we can say the current is behind the source voltage. You see? The current is behind the source voltage and the inductor voltage by pi over 2 radians. You see? Behind the reason why it's negative pi over 2. So then to do a phasor diagram for this, how would we do that? So if I draw the voltage of the resistor, not resistor, I mean voltage of the resistor, sorry, voltage of the inductor and voltage of the source, they're equal, right? So what would the current look like? The current would be behind them, behind both of them by pi over 2 radians. So as this thing is rotating, see when this thing reaches its, goes like this, it reaches its max, the current goes like that and is 0. You see that? The current is 0 when the source voltage is its max. Then as this goes like this, like this, like this, this guy, and is like that, 0, then the current goes like that, and then becomes vertical. So then that's this point right here. You see, the current is max, the source voltage is 0. So you see this, the rotation of this is mimicking every single point of the wave of both of them. Is this something you've encountered, Daniel?
Sadly, no. The phasors are kind of new to me.
New?
Yeah, the phasors are a little new to me. Yeah.
Yeah, so you could ask questions as I'm explaining, and then I'm sure other people are may also have those questions. So it would be, if something is comes up in your mind, feel free.
Yeah, for sure. I mean, right now I was just looking at the whole phasor diagram, and it makes sense too. Like, you said, right? Like those two vectors are pretty much moving at the same rate with each other, but they're perpendicular, right?
Yes. In other words, the nature only knows about this. It tells you, oh, okay, if this oscillation of the source voltage is this, the oscillation of the current. But this is something we've invented to be able to visualize this more easily. And say, oh, okay, this is rotation. And then their vertical components tell us what their magnitudes are. So if this thing is like that and the current is like that, then the source voltage has reached its max. That's this point. And then at that point, the current is like this. So its vertical component is 0, which means that's right there. It's weird.
Yeah.
Yeah. And now you could say this guy started when it was like this, and then the current was down like that. And then that's this point when it was negative. Okay, now we do the resistor. Okay. Oh, I mean, not resistor, capacitor. So with capacitor, you're going to get V source minus Q over C is equal to 0. And then you're going to say V source is Vm sine omega t is Q over C. And then C goes up to there. You have CVm is equal to CVm sine omega t is Q. So in other words, for the capacitor, we're given the charge as a function of time, the charge on the capacitor. Now, if I want to know the current as a function of time, I take its derivative. You see, it's opposite. Here, I know the di dt, and then I integrate it, whereas there, I know the q, and I differentiate it. So now I'm going to say the current is going to be dq dt, and then the derivative of sine is cosine, and then the omega will come out. Okay, so now how will that look? So on the oscilloscope, the source voltage will look like this again. V source, and it will also equal to V of capacitor. Now the current will be a cosine function, negative, not a negative cosine. So the current will start over here and be positive. Then it's going to go like this. Then it's going to go down. When this is 0, that one is its minimum. Then when this is 0, that one reaches, then when this is negative, this reaches 0. And then when that reaches 0, this reaches maximum. Okay, so you can kind of project almost what's going to happen, because if the current is behind on this one, it's most likely ahead on this one, right? So then it's going to be, this one is going to be pi of t omega c Vm sine of omega t plus pi over 2. Yeah, so you see, if you put 0 here, you get 1, and then if you put 0 here, you get 1 also. So this, the current is ahead of the source voltage and the capacitor voltage. So you could say current in a circuit is ahead of the voltage of the capacitor and the voltage. Well, you know what? Let's make that generalization. Current in a circuit is ahead of voltage of capacitor by pi over 2 radians. And then over there, the current in the circuit, is behind voltage of inductors. You see, and then the phase diagram for that is going to be voltage of capacitor equals voltage of source, right? And then the current is going to be ahead. Okay, now one way you can kind of see just by graph who's ahead, who's behind, is to say the current reaches its max before the source does. Then current reaches 0 before the source does. You see? So it's always ahead of it. And this difference in the time is a measure of their phase angle difference between each other. Oh, you see, this reaches 0 before this guy does. It reaches its max before this guy does. So this is the difference in the time. So that difference should stay constant. You see, the delta T. This reaches minimum before that guy does. So you see this difference in the time. Because we're plotting voltage of the source and the current as a function of time. You see, so that's the difference in time when they are reaching the same condition, either max or 0 or min. See, in the other one, the voltage of the source is ahead because it reaches 0 before the inductor does. So, I mean, before the current. So, in other words, the source voltage reaches 0 before the current does. So, you see, this is also delta T. And then it reaches max before the inductor does. So, this is also delta T. And that delta T should stay constant throughout the progression. Then it reaches 0 again before this guy does. It goes like that. Okay, so the other thing that we can, the other thing that we could conclude from this also is, let's see here. Oh, the current, by the way, in a resistor, we can say the current is in phase with the voltage of the resistors. You see, they're both doing the same thing. The other thing we can conclude is this thing here. What is this thing? Omega L. You see, for the resistor, we have Vm over R. In other words, this graph is smaller than this graph by a ratio of the resistance of the resistor. Well, this thing here must be a measure of the resistance of an inductor, right? So it must be a measure of how much an inductor resists changes of current, right? And therefore kills the current by that amount. So this is called inductive reactance, XL, and it's omega L. If we analyze the units of this, it should come out units of ohms. Ohms. Because it's a measure of how much an inductor resists current in an AC circuit, you see. The bigger the omega is, the bigger the inductance is, the more the current is smaller, you see. So what are the units of this, if we were to analyze? This is radians per second. And remember, Henry's was ohms seconds. You see, that's it. Second cancel. And you have radians is really not a unit. So you have ohms. There you have it. You see. So why is that? Why is inductive reactance omega L? In other words, why is it true that the faster I try to change the frequency, the bigger I try to change that, faster I try to change that, and the bigger the L, the more the current is smaller. You see, it has to do with something what we mentioned Wednesday at what an inductor is, right? Remember what inductors don't like? You see here, inductors don't like quick changes of current, and so they resist you. So the inductors are the electrical equivalent of inertia. They don't like change. You know, it's kind of like the COVID thing. Whoever has a lot of inertia didn't want to change very fast. So they resisted it. They resisted it wearing masks and all of this, right? So they would be an inductor. So too many quick changes in society, which is kind of like saying omega is high. So if you're an inductor, if the omega is high, you resist, you know, too many changes, you start protesting against that change by not wearing masks or whatever, you know. But for a capacitor, look at its resistance. It's opposite. So for a capacitor, what did the current come out? I of t is omega c Vm. So then this guy has to go to the bottom, 1 over omega c. Okay, so therefore, capacitive reactance is 1 over omega c. Xc is 1 over omega c. That's capacitive reactance. So with a capacitor, it's opposite. The smaller the frequency, the smaller the C, the more it resists the flow of current. It kills the flow of current. That is weird. This is XC. You see, we could replace this by XC. So this must have units of ohms. Let's check that. 1 over radians per second. What's this? Farads. What's a farad? Coulombs per volt. Right? Yeah, farad is coulomb per volt, and omega is rad per second. And what does that come out? Coulomb per second is an amp. So that's 1 over an amp over a volt. And then volt goes to the top. Volt over an amp, that's resistance. Oh yeah, ohms. Yeah, 1 over omega c has units of ohms. So what this is telling you, the smaller the capacitor and the smaller, the less you change, the frequency, the smaller the frequency, the more the capacitor resists the flow of current. You see? So why is that? That's weird. In other words, the other one seems to be more intuitive, that if you change the frequency a lot, it doesn't like change, so it resists you. But this is the opposite. The slower you change the voltage, the more it resists you. Why is that? Right. So in other words, by saying omega is small, what are we saying? That this source voltage is going up and down very slowly. So for omega small means that it's going like this, like this, like this, you see. So it's taking a while for this source voltage to build up to positive. Then it's decreasing, then switching to negative. Well, what's happening? If you try to charge a capacitor that way, you're giving a chance for the capacitor to get charged, right? So if you're not switching the charge very, very quickly, like this, right? You're giving a chance for that capacitor to charge. You're saying, oh, okay, I'm going to charge you. Right? And then when it gets charged, what does it do? It starts to fight against the current, you see? So look how long it takes for the battery voltage to stay positive, you see? Then it starts going negative, which means it starts taking back the negative, it starts discharging the capacitor, you see? So if the omega is small, you've been charging it positively for a very long time. Well, that's what the capacitor loves. The capacitor wants to store charge and therefore fight against the current, you see. So that's why when the omega is small, that's when the capacitor kills the current. But here it's opposite. When the omega is small, the inductor is like it doesn't even exist because the IDT is very small. Okay? That's why an inductor and a capacitor are sort of used together in tuning circuits, because this guy resists the flow of current for low frequency, for high frequency, and then this resists low frequency. And together they can be used to tune the circuit to whatever frequency you want, like in radio tuners. God, isn't that crazy? All this theory, but then it all comes back down to some application. Okay, so now let's see what would happen. Oh, now let's talk something about root mean square voltage. Root mean square, RMS voltage, and current. So if we go back to the very first one, where we had just the resistor, and what was the, we had the current in the circuit was Vm over R sine omega t, right? Now let's talk about something known as root mean square voltage and current. What do we mean by that? So to do that, let's analyze the power of the circuit. The power of the resistor, the power lost in the resistor is going to be what? Power of resistor, I squared R, right? So then it's going to be this thing squared. Sine squared omega t. So now if I want to find the average power, so in other words, the power as a function of time, the instantaneous power is going to look like this. So it's always positive. You see, so then the maximum value of it is Vm squared over R. Right, so now Vm squared over R. So now if I want to find the average value of that, what do? I integrate this in one period. So the average power is going to be Vm squared over, oh no, I forgot to multiply this by R, right? By R. And then the R and the R cancels. Yeah. So then you got Vm squared over R sine squared omega t dt from 0 to period t over one period of the motion. And the period is 2 pi over omega. Vm squared over R, 2 pi over omega. And now the sine squared is going to be what? 1 plus cosine of 2 omega t over 2. Is that the double angle formula? Sine squared double angle sine squared sine squared A is 1 minus, 1 minus cosine of 2A over 2, right? 1 minus cosine 2A over 2. Ah, okay. So when we want to integrate sine squared, one of the things we do is use the double angle formula. It's 1 minus cosine of 2 omega t over 2. Now we can integrate that. 0 to the period dt. P average R Vm squared over R. Okay, now we're going to have the 2 can come out. Then the integral of 1 is just going to be t. And the integral of this guy is going to be negative sine 2 omega t over 2 omega. From 0 to, and then the period is 2 pi over omega. Over 2 pi over omega. Okay, then you can put that in here. Vm squared over 2r, 2 pi over omega, minus sine of 2 omega, 2 pi over omega, over 2 omega. Then when you put 0, that just becomes 0, and the sine of 0 becomes 0. So that's it. Over 2 pi over omega. So I'm trying to mathematically find this average value of the sine squared function. This is a sine squared omega t within one period from here to here. This is one period. Okay, then what's going to happen? This is going to be omega, omega going to cancel. So you're going to have sine of 4 pi, which is 0. And then 2 pi over omega cancels 2 pi over omega. Okay, then that's gone. Okay, then you're left with this. So that means that the average power during one cycle of an AC, the average power output is equal to half of the maximum. This is 1/2 Vm squared over R. So that's pretty easy. Okay, so the average power is 1/2 Vm squared over R. Okay, so now what's the effective, therefore, what is the effective voltage of the source? The source voltage was what? Vm sine of omega t. So what's the effective voltage of the source? Okay, the source, the maximum voltage of the source is Vm. But the effective voltage is not really Vm, because in a DC circuit, right, in a DC circuit, what would the power have been? Power would have been Vm squared, V battery squared over R, right? So there would be no 2 in that function. So in other words, if we want to rewrite this like this and compare an AC source to a DC source, we can say, take the 2 inside of the Vm and then rewrite it like this. Okay, then this thing we can call the effective voltage, the effective voltage of an AC source, because it resembles the equation for a DC battery. Power of a DC source is VB squared over R. So this thing is what we call the root mean square of an AC source, Vm over root 2. So in order to measure the source's root mean square value, we usually take a multimeter we put it in AC mode. There's a little button that looks something like that, AC mode. Then we connect it across the source voltage, and then that will give you the root mean square velocity, the root mean square voltage. See, I even had a slip of the tongue, root mean square velocity from thermodynamics, but this is different. It's loosely related to that, but not really. So if you put this DC, on a DC mode and put it across the source, it's going to show you 0. Because what it's going to do is it's just going to take the power like this, and it's just going to average it out, and it's going to say 0. So that doesn't mean anything, right? So you have to put it into AC mode. Then what it's essentially going to do is square these values. Then average that, right, which you get half. Then square root it. Then you get 1/√2. Then that's what it gives you. The multimeter gives you the root mean square voltage. So when we say the power in America is the voltage in America is 110 or 120, right? In the US, it's 110, 120, and then in Europe it's what, 220, 240 is it? Something like that. Both of those values are the root mean square voltages. The root mean square voltage is 120. And then in Europe, the root mean square voltage is 220 or 240, right? So it's not the maximum voltage. If you want to calculate the maximum voltage, it would be this times √2. The max would be 120 √2, which gives you what? 169.70. And most of our power is in a frequency of 60 cycles, right? 60 hertz. See, in North America, the most common combination is 120 volts. That's the root mean square voltage, and a frequency of 60. Other voltages exist, and some countries may have, for example, 230 and 60 hertz. I guess they're all 60. Why? I wonder why the 60 came. What's the purpose of the 60? Most of the United States uses electricity at anywhere from 110 to 120. The electronics we build are designed so that they can handle the slight power variation without malfunctioning. By contrast, Europe and most of the world uses power at 220 to 240. What frequency is used? 60. How about the other parts of the world? In the world, what is the frequency? The world runs in one of two electricity frequencies, 50 or 60. It's not a concern unless you have a clock or a device where the clock function is critical. Most devices are designed to accommodate a range of frequencies. The power label on that type of device will say 50 to 60 hertz. Oh, okay, so you guys get it? So, in other words, frequency everywhere in the world is either 50 or 60, but you don't need to adjust for that. If you take your electronic equipment to Europe, it should be able to handle 50 or 60. But of course, for voltage, you need to step it down from 220 to 120 to lower voltage sockets. Oh my gosh, A, B, C, D, E. It's a headache. Why so different, right, from each other? Oh my gosh. I like this one. Two slanted ones. It's like almost like a face with a mouth. It's like emojis, right? It's funny. Okay. Okay, so you kind of get that idea of the root mean square. It's a little similar to the velocity root mean square, which is like you're squaring the voltage of the source, then taking its average, then square rooting it, and then that's where the 1 over root 2 comes from. Okay.